Crab Nebula, 25 years apart, a visual analysis. So let's take a look at these two images. First, we'll take a look at 1999, and then we're going to fade in 2024. So you could clearly see there was some action going on there. We're going to analyze these two images. So our agenda. First off, we'll take a look at the history of observing the Crab Nebula. Then we'll take a 4-image sequence so you can see the expansion of the nebula over time. Then we'll do a deep dive onto one spot on a pair of Hubble images. Those are the 1999 and the 2024 images. And using our analysis, we'll make some parametric equations and stick them in Geogebra. And then we're going to catalog 6 more spots for a total of 7 spots in the original images and put them all in Geogebra. So once they're in Geogebra, and we're going to wind back the clock to see if we could figure out the origin of the Crab Nebula. And then just for fun, we'll take a look at how big the Crab Nebula is. So, brief history of observing the Crab Nebula. So way back in 1781, Charles Messier published his catalog, and he made the Crab Nebula the first item in his catalog, M1. And he was an interesting astronomer. He was an amateur astronomer, but he loved hunting for comets. And the thing about a nebula is it looks kind of fuzzy, kind of like a comet might. And so he wanted to make a catalog of all these nebula, and star clusters, so that people wouldn't mistake them for comets. And it's in French, but you can kind of make out what it says about, above the southern horn of Taurus and other details. And over here on the left, you could see right ascension and declination for each of the objects. And that was way back in 1781 was the first version of his catalog. Then in 1844, the first image we have of the Crab Nebula was actually a drawing done by William Parsons. And then let's fade in the first photograph of the nebula in 1892 by Isaac Roberts. And then this is done by an amateur astronomer, Mauri Rosenthal. He actually describes how he photographed the nebula. And then let's take a look at a real detailed version from the European Southern Observatory's VLT, the Very Large Telescope. And this was from 1999, and the same year, it was imaged by the Hubble Space Telescope. And just look at that detail. It's pretty insane. So let's go through a sequence of images showing the expansion of the nebula over time. So I really tried hard to line up the background stars. So if you look at this sequence of images, it kind of looks like we're zooming in, but we're not. It's literally the nebula expanding over time. So we're going to start with 1942, 1976, 1999, and then 2024. And again, it kind of looked like it was zooming in, but if you focus your eye on a background star, you can see the nebula is the one that's expanding. So let's do it a little bit faster. 1942, 76, 99, and 24. And then one more time, a little faster still. All right, so we clearly see the nebula is expanding over time, and that's what we're really going to be taking a look at. We're going to just, first off, we're going to take one spot in a pair of Hubble images 25 years apart. So it doesn't look like there's much there, but I really just wanted to find like a single pixel that I can zoom in on. So I'm just labeling that A, and then 2024, you can kind of see that one little pixel, it is moving. The background stars are not moving. So we're just gonna analyze that. So there that is. You can probably see that spot a little bit better, just a little pixel. And so what I did is I figured out exactly what pixel that was, and then in 1989 and then 2024. So then we're going to feed those things into parametric equations, or we'll figure out the parametric equations, and then we'll feed them into Geogebra. So let's just start off with x. We're going to say x is changing over time. So let's take a look. The change of time is 25 years. So our delta t is 25, and our delta x is just a mere 2 pixels, which is kind of funny. It's moving 2 pixels in 25 years. And from this, we can write our first pass of the parametric equation, starting at the year 1028. I'm sorry, starting at pixel 1028. We're going to add 2 pixels per 25 years. And we're going to multiply that by how many years. So how many years since 1999? You could represent that as t minus 1999. So this is our first parametric equation, which we can then check out. What if t does equal 1999? Well, 1999 minus 1999 is 0, and 2 over 25 times 0 is also 0, and we end up with 1028. So our first value works out. But what about at the year 2024? Well, 2024 minus 1999 is 25, and 2 over 25 times 25, that's just 2. And so we end up with 1028 plus 2, which is 1030. All right. So our parametric equations works for our two locations, our two x value locations. Now we can repeat the process with y. But first we'll put that equation into GeoGebra, and then we'll repeat the process with y. Now the y value is going down. As time goes up, y value goes down by 9 pixels. So we're going to have a negative 9 over 25 in this formula. But the rest of the formula is very similar. Again, our starting value was 208. And so we could plug this into GeoGebra as well. Now, the whole thing about parametric equations is they're both relative to t. So you can manipulate time, and then you can see the x and the y coordinates from that. So we need to plot a point on the screen. So we'll say our point A is the x of t, comma, the y of t. All right. And if t is 2024, that point would be at 1030, comma, 199. All right. So that is one point. And now we're just going to repeat the process with 6 more points, 6 more spots. All right. So again, here's our spot A. And here are the other 6 spots. And again, you can see each one of those is a little bit of imagery that is moving slightly. All right, so if we figure out the values, if we catalog the values of those things in 1999 and 2024, we could put them into a catalog of 7 values. And then I enlisted the help of Grok to help write the parametric equations for those 7 points. And then I plugged them into GeoGebra. All right. So GeoGebra will calculate all the points and then draw the points on the screen. Now, one problem is that when we're taking a look at these pixels, in graphics, the origin is the upper left. So 0, 0 is the upper left of any image. Unfortunately, on the Cartesian coordinate system, when dealing with positive values, the origin is the lower left. So I had to take the image of the nebula and just invert it vertically. It's essentially a mirror image. So plugging in all the points, those 7 yellow dots are actually drawn by GeoGebra. Those are the spots that I had selected. And the very top of this is a slider where we're starting off at t equals 2024, and we will go back in time to see if we can figure out the origin of the Crab Nebula. All right. So that's what we're going to do next. We'll try to find our time 0 by minimizing those cluster of 7 spots. Now, we're going to run into a problem. When you're dealing with statistics, if you have a set of data and there's some space between points, interpolation is pretty safe. You can run into some problems, but it's pretty safe. If you have data on the left and data on the right, and then you just kind of go, partially through the data, it's pretty safe to interpolate. But extrapolation is where you're trying to figure out something that is outside of known values. And this, you should really use great caution, because the data can really, get problematic, and the data can go, skew in one direction or another. And also, it really depends on the accuracy of your original data points. So we are not going to have a perfect response. So when we do this going back in time, all of our spots are not going to end up at a single pixel on the screen. They're just going to cluster. So we just want that cluster to be as small as possible. So here is where we're going to drag the slider. So if you take a look at the slider at the top of the screen, we're going to drag it. And I'm just going to first go just one click to 1999. So we have 2024 and 1999. And now let's drag back in time. Oh, I went too far. Come back. Went too far again. All right, let's settle down. Let's try to kind of go back and forth to see what is about right there, 1049. So that, just by my eyeball, that looked like it was the smallest cluster of dots. So we're going to go with t equals 1049. So our conclusion is, extrapolating all those data points, that the year of origin of the Crab Nebula should be around 1049 AD. And so you could write that, being that my increment was 25 years, so basically 1049 plus or minus 25 years. All right, so we want it to be somewhere in the interval of the year 1024 and the year 1074. And you can draw that with error bars. All right, so I'll be happy if the actual origin is somewhere in that zone. And it turns out that was 1054. So this is actually a famous event in history. The year around 4th or 5th July, 1054, is where that star went supernova, creating the Crab Nebula. So I think I did pretty well with my estimate. So I'm quite pleased with myself. Now, just to show you how ridiculous this extrapolation was, the two red points on the far right, that is where our source data was, the year 1999 and the year 2024. And my estimate was 1049 all the way over on the left. And I was pretty darn close. 1054 was the actual event. Now, the story gets more interesting. There is a cave painting, or more like a cliff painting in Chaco Canyon from the Pueblos. And it quite possibly may be depicting this event. So this cliff faces east. So if you are looking at the cliff, you are facing west and you cannot see the sky. So what you do is you back up against the cliff, right? You back up against the cliff so that you are facing east, and then you can look up. But what I did is I went into Starry Night, and I dialed back until I got to July 5th, 1054. And you see that if you're facing east, the crescent moon, very, very small crescent moon, is right next to the location of the nebula in Taurus. So if we were to back up against the cliff and look up, this is the orientation. So we are now facing east, and we're looking up at the overhang. And so I think that's a pretty good representation, because it is a very, very thin crescent moon, and the nebula is literally less than a degree away in the sky. And so I think that's pretty convincing, or at least it's a very close correlation with the cave painting. So just for fun, how big is the Crab Nebula? So let's just zoom into a little strand of filament, and let's zoom in some more until finally we're just looking at 1 pixel from the original source image. Now, what is that little circle that I've drawn? Is that circle the size of Earth? No. Is that circle the size of the sun? No. That circle is Neptune's orbit. So basically our entire solar system is 1/15 of 1 pixel in that image of the Crab Nebula, which is just jaw-droppingly, ridiculously hard to get your mind around. All right, that's all I got for you. So please be kind to each other in the comments. Bye.